Hello everyone. The title of this video is Factoring by Grouping. Now every example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org, and I'm in their Algebra and Trigonometry text in section 1.5 titled Factoring Polynomials, and I'm looking under the heading Factoring by Grouping. Alright, so all the examples I'm doing are taken either from the examples or the try it boxes in the reading, or from some of the even numbered exercises at the end of the section that are related to this particular objective. I will have timestamps for each example in the description of the video below, so look out for those. And I would also request that when I start a new question in the video, pause it and try to work it out yourself first before watching me do it and comparing. Because if you're just watching me do these things and not practicing yourself, chances are you're not learning all that much. Alright, so the first example where we're asked to now we're going to be factoring, for the most part, trinomials, quadratic trinomials by grouping. And again, we're just asked to factor here, meaning, rewrite the expression that you're given as a product, right, as a multiplicative expression. So we're starting with 2x squared plus 9x plus 9. Alright, so here's the method we're going to use. I'm going to go off to the side here and write out the steps I'm going to follow for every single example in this video. So we're going to be factoring expressions of the following form. It's going to be some number a, that's usually not 1, times a variable squared. Right, like I said, we'll be looking at quadratic polynomials, degree 2 polynomials, so the highest power on the variable will be 2, plus b, some number b times x, plus, and then some number c, right, where a, b, and c are real numbers. Right? For the most part, they're going to be integers, but integers are real numbers. Obviously, a is not 0, okay? Because if a were 0, then it would just be a linear polynomial. There'd be no quadratic term. And of course, the variable is x or some other variable. We're going to see examples where the variable is not x, but you have a number times a variable squared plus a number times that variable to the first power plus another number. All right, we're going to factor this by grouping, this method called grouping. All right, so the first step is find the product a times c. All right, so you're going to take the lead coefficient, multiply it by the constant. And this particular example, a, the quadratic coefficient, is positive 2. B, which is the linear coefficient, is positive 9. And C, which is the constant term, is positive 9 as well. So first step, I'm doing A times C. Right, so we would do 2 times 9 equals 18. And of course I failed to mention that the first step you do whenever you're factoring is pull out the greatest common factor, the GCF, but I'll tell you right now, the examples in this particular video, we won't have to worry about that. There is no greatest common factor to pull out other than 1. Alright, so first I find a times c, so here at 18. Then we're going to find a pair of factors of this AC whose sum is b. In other words, we want the following. Now I'm going to call this pair of factors p and q. So we want to find a p and a q, so a number p and a number q, such that p times q is the same as a times c, and at the same time p plus q is equal to b, right, the linear coefficient. Now I'll put a little note here. If these can't be found, right, if these cannot be found, then we're just going to consider the polynomial prime. And the polynomial is prime, meaning it can't be factored over the integers, right? When we talk about factoring, I want to be able to factor things so that all the coefficients are always integers, right? So when we say it's prime over the integers. Alright, so let's see if we can do that here. Can we find factors of 18? So I'll make a little chart. Pairs of factors of 18 along with their sums. And 18 is positive. So if I'm looking for two factors, they either are both positive or they're both negative, right? Because positive times positive is positive. Negative times negative is also positive. But I want a sum of 9, positive 9. So I need two positive numbers, right? Two negative numbers are going to add up to a negative number. So when I list my pairs of factors, it's just going to be pairs of positive numbers. So how about 1 and 18, right? Those multiply to be 18. But they add to be 19. So no, right? That's not 9. How about 2? We saw 2 and 9, obviously. But those add up to be 11, not 9. Right? So no on that pair. 3 and 6, right? 3 times 6 is 18, and 3 plus 6 is 9. Yes, this is the pair that we wish for. Right, this is the pair that we want right here. This is I'll call them, P and Q. Right. 3 times 6 is 18, which is the same as A times C. And 3 plus 6 is 9, which is B. Alright, then the next step, third step, going to rewrite ax squared plus bx plus c as ax squared plus px plus qx. Alright, so you're just rewriting that middle term. Rewriting bx as px plus qx, right? And, again, p and q are those factors of a, c that add up to b. And then you still got the plus c. Right? So 2x squared, right? 2x squared plus 9x plus 9, the quadratic term and the constant term are staying the same. You have 2x squared, and then you have plus 9. It's the middle term. It's the linear term that you're rewriting. Positive 9x, I can rewrite as 3x plus 6x. So it's 2x squared plus 3x plus 6x. Right? Do you see how those two numbers, right, they add up to 9? 3x plus 6x would be the same as 9x. So this expression here is equivalent to the original expression. So we're still good. Alright, so now more steps. I'm going to go to the next page. Alright, then we're going to perform something called factoring by grouping. Where I break, now for these polynomials here, what you do is you break the polynomial up into two groups. Now there are four terms, right? Four terms in this, so you could do 3 and 1, 1 and 3, but I'll tell you right now, for our purposes, it's going to be 2 and 2. So I break it up into groups. So I put the first two terms in one set of parentheses in one group, right? The ax squared plus px, and then I make a big plus sign, and then plus for the middle plus, and then in a second separate group, I put the next two terms, right? Qx plus c. So you break the polynomial up into two groups. So let me do that with my example here. I'm putting the first two terms in a group in a set of parentheses, right? So 2x squared plus 3x, big plus, and then the next two terms, 6x and 9, right? 6x plus 9 in their own group. Right? Then you factor out the GCF of each group. Remember, the greatest common factor of each group. Alright, and then another thing to keep in mind here, sorry about all the side notes, but a side note to this, if lead coefficient is negative in one of these groups, factor out, pull out the opposite of the GCF, right, or a negative GCF, right? But we're not seeing that here, right? In this first group, the lead coefficient is positive, positive 2, and in the second group, the lead coefficient is positive, again, positive 6. So I don't have to worry about that just yet. Alright, so for this first group, I'm hoping you remember how to find the greatest common factor of a couple terms. For 2x squared and 3x, the greatest common factor is just x. Alright, so I pull that out. So this is equal to x times, and then remember what's left over when you remove x would be 2x plus 3. Alright, so there's the first product. Plus, and then the second group, I do the same thing. The 6x plus 9. What's the greatest common factor of that group? Well, that'd be 3. Alright, so I pull 3 out. And then what's left over in this group when I remove a factor of 3 would be 2x plus 3. So you factor out the greatest common factor of each group, and then you factor out the greatest common factor of the entire expression. Factor out GCF of entire expression, and this should be good. Right? So now if you look at the entire expression, I've got, two terms. Remember, a term is a product, separated by plus signs. So there are two terms now in this expression. There's this product here, x times 2x plus 3. Remember, if something is in parentheses, that's considered a single factor. So there's a factor of x and a factor of 2x plus 3 in this first term, plus, and then the next term has a factor of 3 and a factor of 2x plus 3. So you notice that they both have a common factor, and that would be the greatest common factor is 2x plus 3, this quantity 2x plus 3. They both have that in common. So I factor that out. So the greatest common factor comes out, 2x plus 3. And then the other factor, right, another quantity, would be what's left over in those terms when I remove 2x plus 3. And when you remove 2x plus 3 from both of these, you'd be left with x and positive 3. So x plus 3 is the other factor. And there we go. Right, this is a product. Right, this is a product. Factor 2x plus 3 times factor x plus 3. So I have factored our original expression. So going all the way back here. So 2x squared plus 9x plus 9 is equal to 2x plus 3 times x plus 3. And don't forget to check. Now I'll show you a couple ways to check. Right. One is you check by multiplying. Right? You check factoring by multiplying. So you take what we got at the end there, 2x plus 3, multiply it by the quantity x plus 3, and hopefully I get the original expression back. So remember how to multiply polynomials. You take every term from one and distribute it to every term from the other one, right? You can only multiply two at a time, two factors at a time. So first I'll distribute the 2x. So 2x times x is 2x squared. 2x times 3 is positive 6x. Now I'm done with the 2x and move over to the 3 and distribute the 3 to the x plus 3. 3 times x is positive 3x. 3 times 3 is positive 9. And then combining these like terms, these x to the first terms, we get 2x squared plus 9x plus 9. And look at that. That is the original expression. So, good. Our factorization is correct. All right. Now another way to, now this doesn't prove anything, but it's a way to get a feel for the fact that these are actually equal. Two expressions are equal only when they're the same value no matter what you plug in for the variables. So no matter what you plug in for x, the value of this expression that we started with will be the same as the value of this factored expression that we ended with. Now you can do that by hand with several values of x, but I'm going to show you a website. It's called desmos.com, free online graphing calculator. And let me enter these expressions. All right, so we have just 2x squared plus 9x plus 9. Now off to the right, they're actually graphing the equation y equals. You have the x-axis and y-axis. You may be familiar with this. They're graphing y equals 2x squared plus 9x plus 9 over here, this blue parabola shape. And then I'll put in the other expression, right, the one we got at the end. The quantity 2x plus 3 times the quantity x plus 3. And look at this, right? See, the graph of this came right on top of the graph of the other one, right? Blue, green, blue, green. But look at the tables, right? I'm gonna throw in some tables for both of these. And we'll see, if you compare the tables, that for the same values of x, you get the same values for each expression. Right? The top expression, when x is negative 2, the value of that expression is negative 1. Same thing down here. For the factored form, when x is negative 2, the value of that factored form expression is negative 1 also. And you could plug in whatever you want for x, and you'll get the same value, matching value for both of these, no matter what you plug in for x. And that should happen if two expressions are truly equal. They'll have the same value no matter what you plug in for the variables. Now that doesn't prove anything, right? What I showed you on those tables, that doesn't prove that they're equal, because they should be equal for all infinitely many value of x you can think of. But if you see that these are equal for 5 or 6 different values of x, then there's probably a good chance that they're equal. I mean, that you can believe it. But this is a more valid way of checking right here, right? Checking by hand, actually multiplying it out and seeing that you get the original expression back. All right. So for the rest of the video, I am following these same steps, and I'll read them off again. So first we find a times c, right? The lead coefficient times the constant. Then we're going to find a pair of factors of ac whose sum is b, if we can. Right, if we can. If we can't, if you go through all possible pairs of factors and you still can't find it, then we're going to call we're going to say it's prime. It can't be factored any further. But if you can, right, if you can find this pair of factors, then you just rewrite the middle term right? Rewrite the middle term using that pair of factors as a sum of two terms, and then break the polynomial into two groups, factor each group, factor the GCF out of each group, and then factor the GCF out of the final expression, right? So a lot of steps, but it'll work every single time. All right, so next example. So same structure for the polynomial, right? It's ax squared plus bx plus c, where the value of a is 6 and the value of b is positive 1, right? That's 1x. And the value of c is negative 1. Right? All right, so that first step in factoring a polynomial like this, a quadratic trinomial, was find a times c, which is 6 times negative 1, which is negative 6. Right? And then I'm trying to find pair of factors of negative 6. Right? So I'll make a little chart again, a little table. Now if you see it already, you don't need to make this table. Like, I already see what factors I'm going to need, but this is for teaching purposes, so I'll do this. I'm looking for a pair of factors of negative 6 that have a sum of b, have a sum of 1, positive 1. Now, two numbers that multiply to be negative 6, a negative number. So that means one's got to be positive and one's got to be negative. But I want their sum to be positive, right? So I want the positive number to have a larger magnitude than the negative number. That way when you add them, you'll get a positive result. For example, negative 1 and positive 6, those multiply to be negative 6, and you see the positive number has a larger magnitude or a larger absolute value than the negative one, right? 6 versus 1. But their sum is 5, right? Negative 1 plus 6 is 5, so no on that, right? That's not the pair I'm looking for. Then negative 2 and positive 3, right? Those multiply to be negative 6, and when you add them, you get positive 1. That's exactly what I'm looking for. All right, so this pair of numbers, negative 2 and positive 3, this is the pair of numbers that I'm going to use to rewrite that middle term. And here's how. So 6x squared plus x minus 1 is 6x squared. And then instead of plus 1x, I'm going to write minus 2x plus 3x. Minus 2x plus 3x. See? Using that pair of numbers to rewrite the middle term. And then we still have the constant term, minus 1. Right? And now comes the grouping. Right? So in a set of parentheses, I put the first two terms, 6x squared minus 2x. And then I like to put a big plus sign, and then another grouping where I put the next two terms, positive 3x and negative 1. Right. Now the first group, the greatest common factor is 2x. So I pull 2x out, and if I do that, what's left over would be 3x minus 1 plus. And then here, when there's nothing in common, I guess I should write it, right? The greatest common factor of this first group was 2x, right? So I pulled that out. I don't see anything in common here. They don't have, other than 1, right? If they don't look like they have anything in common, every term has a common factor of 1 at least, right? So the greatest common factor there would just be 1. So you could pull that 1 out if you want. I mean, you don't really have to write it. Anything times 1 is itself. But I'll put the 1 there. Why not? Put the GCF out there. And then you still have 3x minus 1, right? I didn't really pull anything out except 1. And then you look at the whole thing. Right? Look at it as a whole. And you have two products, two terms. And these terms have a common factor of 3x minus 1. That's the GCF. Right? The quantity 3x minus 1. So that comes out. So 3x minus 1 times, and then the other quantity, the other factor, is what's left over when I remove 3x minus 1, which would be 2x plus 1. And there you go. There's a product. right? This polynomial I started with is now factored, right? Written as a product. 3x minus 1 times 2x plus 1, or 2x plus 1 times 3x minus 1. Please understand that the order that the factors come in does not matter, right? Multiplication is commutative in the real numbers. And please don't forget to check, right? You can check in the ways that I showed you for example 1. Multiply this out. Distribute the 3x to the 2x plus 1, then distribute the negative 1 to the 2x plus 1, and combine like terms, and you should get 6x squared plus x minus 1 back. Right? And I leave it to you to check. And once again, you could also test it out with a few values of x, right? These expressions should have the same value no matter what you plug in for x. And I'll leave it to you to test that stuff from here on out. All right, great. Next question. All right, so example 3, same start. 6x squared plus 5x minus 4, right? That's in the ax squared plus bx plus c form. So a times c here, again, it's just a lead coefficient times the constant. 6 times negative 4 is negative 24. The pair of factors I'm looking for, again, you can make a table if you want, but the pair of factors I'm looking for, I want these numbers to multiply to be negative 24 and add to be positive 5. So that's negative 3 and positive 8. All right, negative 3 times 8 is negative 24. Negative 3 plus 8 is positive 5. All right, and now I'm going to use these numbers to rewrite the middle term. So this 6x squared plus 5x minus 4 is equivalent to 6x squared, and then instead of plus 5x, I'm going to write minus 3x plus 8x. And then you got the minus 4 still. All right, now comes the grouping. All right, so in a set of parentheses, the first two terms, 6x squared minus 3x, big plus sign, and then in another set of parentheses, another group, the next two terms, positive 8x and negative 4. And I factor each group. The first group, greatest common factor would be 3x, so I pull 3x out, and what would be left over would be 2x minus 1 plus, and then 8x minus 4 has a GCF of 4. And if I remove 4, you got 2x minus 1 again left over. And then you look at both of these products, they have a common factor of 2x minus 1. Right, so 2x minus 1 comes out times, and then if I remove 2x minus 1, what's left over is 3x plus 4. And there you go. Right? There's our original polynomial factored, right, written as a product. And once again, I'll leave it to you, but don't forget to check your answers. Multiply these and see if you get the original expression back. Or make sure that these are always equal to each other, no matter what you plug in for x. Wonderful. Alright, so this next example, oh man, the variable's not x anymore. It doesn't matter. It's the same setup. You have a number times a variable squared plus a number times that same variable to the first plus another number. Alright, so instead of writing a times c, because it might be confusing with the c here, I'm just going to put lead coefficient times constant. Right, that's the a times c. Right, lead coefficient times constant. Alright, so here that's 6 times 63. So that'd be 378. Alright, that's 360 plus 18. Alright, and now we're looking for, and this one I might make a chart for, we're looking for a pair of factors of 378 that have a sum of 41. All right. So I'll do that. I'll make a little table. Factors of 378 whose sum. Now, they need to both be positive numbers because I want the sum to be positive and the product to be positive, right? So obviously 1 and 378, that's not working. All right, those add up to 379, which is not 41. This is even, so 2 goes into it. All right, it'll be 2 times 189. Right. And those add up to 191. So we're getting smaller, getting closer to 41, but that's not good. 6, 3 goes into 6, and 6 is a factor of this. So 3 goes into this, right? That'd be 3 times 126. Right. Those add up to 129, getting smaller, but still not there. Now 4, this is 2 times 3, 2 doesn't go into that, 4 doesn't go into this. This doesn't end in 5 or 0, so it's not a multiple of 5. It is a multiple of 6, right? We saw 6 times 63. Those add up to 69, so getting closer, but not quite there. We want a sum of 41. Let's see. Now 7 goes into 63, so 7 is a factor. This is 7 times 9. All right, so 9 times 6, 54. 7 times 54 would be 378. And these add up to 61. So still smaller, but not quite there. 4 doesn't go into it, so 8 definitely doesn't. 9 does. All right, like I said, this is 9 times 7, so 9. 9 times 7. 7 times 6 is 42. Right, and 9 plus 42 is 51. Almost there. Not a multiple of 10. Not a multiple of 11. Not a multiple of 12. Not a multiple of 13. I mean, because we know the prime factorizations of this. This is 2 times 3 times 7 times 9. So 2 times 3 cubed times 7. Right. Oh, there it is. I see it right now. 27 and 14. 14 and 27. Those add up to 41. Aha, aha, aha. Right. So yeah, that's that can be a pain, especially when the numbers are large like that. Now you could use a calculator to help you out. Do some divisions and divide by certain integers, see what factors are what. Writing the prime factorization helps, right? Writing as a product of primes helps to let you know what numbers go into it evenly. But yeah, so this is the pair of numbers I want to use. Right, 14 and 27. So I'm going to rewrite this. Right, again, I'm just rewriting the middle term. So this is still 6c squared. And then instead of plus 41c, I'm going to have plus 14c plus 27c. Right, plus 14c plus 27c. Or the other way around. Again, it doesn't matter what order you add things in either. Right. Plus 63. And then we do the grouping. Right, so down here, so the first two terms, 6c squared plus 14c in the first two terms, and then a big group with the second two terms, right? 27c plus 63. The greatest common factor of this first group, these first two terms would be 2c, and it'd have 3c plus 7 left over, plus, and then here these have a common factor, greatest common factor, the largest one of 9. And then you have again 3c plus 7. And you better hope that this happens, right? That the factor left over in both groups is the same, so that way you can actually factor it in total. Because if these aren't the same, then you're either doing it wrong or it just can't be factored. And you see that both these products here, both these terms have a factor of 3c plus 7. Right, so I pull out 3c plus 7. And the other factor left over would be 2c plus 9. And there you go. There's the original polynomial written as a product, right? Factored. 3c plus 7 times 2c plus 9, or 2c plus 9 times 3c plus 7, same thing. And please don't forget to check your results. Multiply these and see if you get the original expression back. Or, make sure that these have the same value no matter what you plug in for C. Right, they better have the same value no matter what you plug in for C. Wonderful. Alright, so I'm going to keep doing this. Okay, so here 20w squared minus 47w plus 24. There is no common factor right now, so again, that's the first thing you should look out for. Is there a common factor you can pull out right away? But there isn't, so I'm going to do the a times c, lead times coefficient, right? That's 20 times 24, which would be 480. Which, you know what, I'm going to break this down right now to its primes. This is 2 squared times 5, right? 20 is 4 times 5. And this is 3 times 2 cubed, right? 3 times 8. So we have 2 to the 5th times 3 times 5. Right. Oh, and I see it right now. I see it. The pair of factors I'm looking for. Again, you can make a little chart if you want, but I see it. The pair of factors we're looking for two numbers that multiply to be positive 480 and add up to be negative 47. So I need two negative numbers, right? Two negative numbers will multiply to be positive and add to be negative. And that's going to be negative 32 and negative 15. Those multiply to be 480. Right, because 2 to the 5th is 32 and 3 times 5 is 15. Right? Those multiply to be positive 480 and they add to be negative 47. Alright, so now I'm going to rewrite. I'm going to rewrite that middle term instead of minus 47w as minus 32w minus 15w. So we have 20w squared, then minus 32w minus 15w, and then plus 24. Alright, now comes the grouping. Right, in the first group I put the first two terms, 20w squared minus 32w, and then again I like to put a big plus sign, and then the next group, the next two terms, which a negative sign is part of a term, negative 15w plus 24. Alright, and I wrote this note out back on the first example. Alright. If the lead coefficient, I'll pull this page back up, right? I wrote this note here. If the lead coefficient of a group is negative, we're going to pull out the opposite of the greatest common factor. So negative GCF. That's going to happen here. Right? So the first group, the greatest common factor, would be 4w. Right, so I pull out 4w, and then you'd have 5w minus 8 left over. Plus, and then, as I said, this next group, the lead coefficient is negative. Right, the lead is negative, so I'm going to pull out the opposite of the greatest common factor. Now the greatest common factor would be 3, but because the lead is negative, I'm going to factor out negative 3. Right? Again, this is the opposite of the GCF. And if I factor out negative 3, what's left over is positive 5w, right? Negative 3 times 5w is negative 15w, and then minus 8. Negative 3 times negative 8 is positive 24. Right? That's why you pull out the negative GCF, the opposite. So that way, this factor remaining here and this factor remaining here are the same, and now I can factor it as a whole. And if you look at both of these products, they both have a factor of 5w minus 8, so I pull that out. And if I remove 5w minus 8, then you have 4w plus negative 3. Right, 4w plus negative 3 or just 4w minus 3, right? Nobody writes plus negative 3 when they're done simplifying. And there we go. There's our original expression factored, written as a product, a multiplication. And again, please check your answer. Multiply these and make sure you get the original expression back. Right. Also verify that these two expressions have the same value no matter what you plug in for w. Right. So next question, same steps. I'm doing the same steps every single time. 7x squared plus 48x minus 7. Alright, so first I look at all the terms. There's no GCF other than 1, so I'm not pulling out a GCF. Alright, then I do the lead coefficient times the constant, right? 7 times negative 7 be negative 49. Right? And then I'm looking for a pair of factors of negative 49 that add up to positive 48. So I can see it right now. I can see it. This would be a negative 1 and positive 49. Right. These multiply to be negative 49, and they add to be positive 48. All right, so now I'm going to use this pair of numbers to rewrite the middle term. So this original expression is equal to 7x squared, and then instead of the plus 48x, got minus 1x, so just minus x, plus 49x, and then minus 7. All right, now comes the grouping, where I break it in half. Group with the first two terms, 7x squared minus x, plus, and then a group with the second two terms, positive 49x, and then minus 7. I factor each group separately, pull the GCF out of each group. Greatest common factor of the first half is x, and I'd have 7x minus 1 left over, plus the greatest common factor here is 7, and it's a positive lead, so I pull just the GCF out, right? So 7 and then times 7x minus 1. And both of these products have 7x minus 1 in common, so I pull that out. And what's left over when I remove 7x minus 1 would be x plus 7. And there we have it. Our original expression written as a product, right? Factored. And please, I'm going to write this every time, don't forget to check your result. Multiply these. Make sure it's the same as the original. Make sure that they have the same value for any value of x that you choose. Okay, just got a few more of these. Performing the same steps every time. Okay, number 7. 2b squared minus 25b minus 247. Again, I'm taking the lead coefficient times the constant. So 2 times negative 247. So this is going to be negative 480 plus 14, negative 494. I believe, yeah, 480 plus 14. Alright, so negative 494. Alright, and then I'm looking for factors of negative 494 that add up to negative 25. Alright, so this time I'll make a table. I don't see it right away. And again, if you see it right away, go for it. So factors of negative 494 and their sum. And I want them to add up to negative 25, a negative number. So I would like the negative number to have a larger magnitude. So 1 and negative 494 obviously isn't cutting it. Right? Those add up to negative 493, so no on that. 2 obviously goes into it, right? 2 and negative 247 would add up to negative 245. So no, but getting closer to negative 25, right? Let's see. 3 is not going into this, right? Because remember the little trick for that is add up the digits. 13 plus 4, 17, which is not a multiple of 3, so that's not a multiple of 3. It's not a multiple of 4 because this is a multiple of 2. 247 is not. You don't have two factors of 2. It's not a multiple of 5. It's not a multiple of 6. Maybe a multiple of 7. 210 plus 37. No, it's not a multiple of 7. Alright, 490 would be 490 is a multiple of 7, and plus 4 is not. It's not a multiple of 8. It's not a multiple of 9, not a multiple of 10, not a multiple of 11. It's definitely not a multiple of 12. How about 13? 13. Right, because this is 13 times 10 is 130. Then you got 20 for 260. Then 390. And 520. If you do 13 times 40, that's 520. But then you have to subtract 26. So 13 times 38. And there we go. Those are the numbers that I want. 13 and negative 38. Those multiply to be negative 494, and they would add to be negative 25. Alright, so yeah, again, this can be a bit of a pain, especially when the numbers are larger. Use a calculator if you need to. Nothing wrong with that. Okay, so now I'm going to rewrite the middle term. So we have 2b squared. And I'll rewrite it the way I have it here. Instead of minus 25b, I'll go plus 13b minus 38b. And then we still have the minus 247. Then comes the grouping, right? First group with the first two terms, 2b squared plus 13b. And then again, I personally like doing this, where I put a big plus sign. And then the next group, the next two terms, which are negative 38b and then minus 247. And again, we have that case where in this second group, right, the lead is negative. So I'm going to be pulling out the opposite of the greatest common factor in that second group. All right, so the first group, the greatest common factor is just b. Maybe b times and then 2b plus 13. Plus, and then I'm going to pull out, the opposite of the greatest common factor. All right. Now, this is 19 times 2, and 247 would be 19 times 13. So the greatest common factor is 19. I pull out negative 19. All right, and if I remove negative 19, you'd have positive 2b and then positive 13. Okay, and now both these have the factor of 2b plus 13. So pull that out, the quantity 2b plus 13 times, and then what's left over is b plus negative 19, or b minus 19. And there we go. Right, there we go. The original expression written as a product, right, factored. And again, please don't forget to check this. Right? Multiply these and see if you get the original expression back, and you should. Great. All right, here we go again. So 90v squared minus 181v plus 90. All right, so I'm taking the lead coefficient times the constant, right? 90 times 90, that would be 8100. Which, you know what, I'm going to break this up. I know I didn't break that one up because I didn't really know the factors of 247 off the top of my head. But this one isn't so bad. 81 is a factor of this. That's 3 to the 4th. This would be 81 times 100. And 100 is 4 times 25, right? 2 squared times 5 squared. So there's the 8100 written as a product of primes. And then can I get 9? Now I want negative 181, and I basically said the factors already. I can already see it. The pair of factors, sorry, that I need here. I need two numbers that multiply to be positive 8100, but they need to add to be negative 181. So that means I need two negative numbers, right? Because two negative numbers will add to be negative and multiply to be positive. And that'd be negative 81 and negative 100. I said them already, 81 and 100. Those add to be negative 181 and multiply to be positive 8100. Alright, so now using these two numbers, I'll rewrite the middle term. So this is 90v squared, and then instead of minus 181v, I'm going to have minus 81v minus 100v. Right, and then you got the plus 90. Alright, now comes the grouping. Alright, first group, the first two terms, 90v squared minus 81v. Then again, I prefer putting a big plus sign in the middle of the groups, plus, and then a group with the next two terms with negative 100v plus 90. And once again, we have a case like in example 7 where this second group, the lead, is a negative number. So I'm going to pull out the opposite of the greatest common factor from this second group. Alright, so from the first group, the greatest common factor here is 9v. And if I remove 9v, you'd have 10v minus 9 left over. Plus, and then from this, now the greatest common factor would be 10, but I'm going to pull out negative 10 since the lead was negative in there. Alright, so I pull out negative 10, and if I pull out negative 10, you'll have positive 10v minus 9 left over. Right. And now both these terms, both these products have 10v minus 9. So pull that out, right? 10v minus 9 times, and if I remove the 10v minus 9, what's left over? 9v plus negative 10, or 9v minus 10. And there we go. Our original expression written as a product, right? Factored. And please check your work. All right, actually multiply these, right? Distribute the 10v, distribute the negative 9, combine like terms, and you'll hopefully get 90v squared minus 181v plus 90, or you should get that. All right, fantastic. And I got just one more example. This time with a bit smaller numbers, this time. The lead coefficient is 2. The constant term is negative 15, right? 2 times negative 15 is negative 30. And I can already see the pair of factors I'm going to need. All right, again, you can make a little table if you want, but one needs to be positive and one needs to be negative to multiply to be negative 30. And I want them to add up to negative 1, right? The coefficient on the linear term is negative 1. So that'd be negative 6 and positive 5. That's the pair of factors I'm looking for. All right, they multiply to be negative 30, and they add to be negative 1. Right, and now I'll use this pair of numbers to rewrite the linear term. So this is 2n squared, and then instead of minus n, I'm going to go minus 6n plus 5n. And then you still have minus 15. Right. And now comes the grouping. Right. Group the first two terms in a set of parentheses, plus, and then the second two terms in a set of parentheses, and then we factor each group. The first group has a greatest common factor of 2n, so I pull 2n out, and what we'd be left with is n minus 3, plus, and then the second group, the greatest common factor is 5, If I remove 5, you'd have n minus 3 left over again. So both of these terms have a factor of n minus 3 in common. I remove that, right, pull n minus 3 out, and the remaining factor would be 2n plus 5. Right. So 2n squared minus n minus 15 is equivalent to this product, right, the factored form, n minus 3 times 2n plus 5. And once again, I will write, please, don't forget to check your work. Multiply these and see that you get the original expression back. Or, also verify that these two expressions have the same value no matter what you plug in for n. Right? That's the only way two expressions are equal, is when they have the same value no matter what you plug in for the variables. Okay, wonderful. All right, so that was a lot, right? And I did the same steps every single time when trying to factor, ax squared plus bx plus c, right? A quadratic polynomial with integer coefficients. We're factoring over the integers. Yeah, so I did the same steps every single time. I'm hoping that watching me go through these 9 examples here help you in some way when you're asked to factor some sort of quadratic trinomial of that form, ax squared plus bx plus c, on your own. And thank you very much for watching.